yesterday.
Okay. Good. Then you should have no problem. Okay.
I actually don't know anything yet. We literally just got introduced to it because we did integration first
Okay.
because apparently that's really hard. So
I was
now
just,
we just got that introduced.
I was just joking.
Well,
Okay. Any idea how you go about this one? Proof by contradiction.
you start by saying you state the negation statement,
Correct.
which would be the opposite of that. So no greatest odd integer. So there is a greater odd integer.
There is a greatest odd integer. Yeah.
Yeah.
So. Yeah. Go on. You have a hint there.
I begin by
sorry.
saying,
Do you know how you could write an odd number?
2n plus 1.
Yeah. So I'm going to do 2k plus 1. 2n plus 1 is fine. So 2k plus 1 is an odd number. Okay.
Yeah.
And what could you do next?
I don't know.
Assumption, greatest odd integer. So that means that an odd integer of 2k plus 1, let's say this is the largest. So 2k plus 1, let 2k plus 1 be the largest odd integer. Would you just add 2? If we were to add 2 to this, 2k plus 2 plus 1, and factorize out 2. I believe that would show. I don't know what they're looking for. Let's take a look. So they did n plus 2, odd plus even plus odd. Okay, so n plus 2, there's greatest odd integer, n plus 2 is also, so they added 2, n plus 2 is greater than n, and it is odd. It's just so simple that it's difficult to break that down. Yeah, so add 2, and then you just have to show that it's odd. So I would, yeah, okay. What's the last thing you would have to say?
Therefore, then just repeat the statement. There is.
Yeah. Okay. Okay, let's try this one.
N squared is even, then n must be even. So say. So do we just make? Oh, we're gonna write the negation statement. Saying that if n squared is even, then n may be odd.
Yeah.
And then if n squared is even, so n squared. Shall we like? Are you meant to do like n squared equals then an odd number like 2k plus 1?
So we could say, yeah, 2k plus 1 squared.
Equals an even number. Wait.
And so what would be the... okay, go on.
I was going to say anything.
Maybe expand this bracket?
Okay. Yeah.
What did you get?
4k squared plus 4k plus 1.
What could you do next?
I don't know. Factorize it. No. Take a factor of 4 out.
So I think technically take a factor of 2 out. But okay.
2k squared plus 2k plus 1.
And so, well, what does that tell you?
That that's an even number.
Yeah, so 2 times 2k squared plus 2k is a multiple of 2. All multiples of 2 are even.
Then it's plus 1, which makes it odd.
Even. Therefore, 2k squared plus 2k is even. Even plus 1 equals odd. So 2 times 2k squared plus 2k plus 1 is odd. And then last thing.
So if just n squared is even, then n must be even.
Yeah. Any questions there?
No.
Must be even. Okay. Let's see what they did. Yes, okay, so they factorized out 2 and they wrote down much less. Let's see, n is odd, so n equals 2k plus 1, n squared equals that. They expanded it, they factorized out 2 because all multiples are 2 are even numbers. So n squared is odd. This contradicts the assumption, therefore. Okay, so we just need to say this contradicts the assumption. So this one was that. Okay. Let's try this next one.
Okay, so the negation statement would be that root 2 is a rational number, so it can be written as a over b.
Assumption. So root 2 is equal to a over b.
So if root 2 equals a over b, and then square that to get rid of the thing, which is a squared over b squared, and then times the b squared, so you get 2b squared equals a squared. A squared is an even number.
Why Why is that?
Is that all square numbers even?
No. 3 squared is 9.
9. Yeah. Yeah, now I'm stuck.
It's an irrational number. So a squared is a square number.
Yeah. It's 2b squared. That's even, isn't it?
2b squared is an even number.
Is or isn't?
It must be an even number because it's
Yeah.
a multiple of 2.
2b squared is even because multiple of 2. Does that mean... Well, that doesn't really get me anywhere, to be fair.
Multiple of 2. Well, 2b squared, I suppose, is always even because it's a multiple of 2.
Yeah.
A squared is odd for the odd numbers because odd times odd equals odd.
But if 2b squared is even, doesn't that mean a squared is even? It's 2b squared equals a squared.
Well, we are contradicting it, so we've assumed the opposite. So we assumed... in reality, the square root of 2 does not equal to a over b.
Yeah, true.
And so what we've done here is we've almost proven the contradiction. So we've said 2b squared is always even because it's a multiple of 2. A squared is odd for the odd numbers.
Why?
So 2b squared is not always equal to a squared.
Okay.
And I suppose therefore root 2
Is an irrational number.
That's it. I just want to see exactly how they said this. I'm sure they did it a simple way. I think it's because it's an integer. And I think as well, if you were to write it as b squared equals a squared over 2, if you have an odd number and you half it, you get a number that isn't an integer. And we were assuming that they are integers. We'll see. Root 2 is a rational number. Root 2 equals a over b. Also assume that this fraction cannot be reduced further. There are no common factors. So a squared equals 2b squared. This means that a squared must be even, so a is also even. If a is even, then it cannot be expressed in the form a equals 2n, where a is an integer. 2b squared must be even, so b is also even. If a and b are both even, they will have a common factor of 2. This contradicts the statement. That's what I was thinking. Just want to see if our one was fine. I think our one was fine. Let's see. Yeah, so the way they went about it was by saying with odd and even. So they said 2b squared. Yeah, they said if a squared is an integer, then a must also be an integer.
Yeah.
No, our way is fine. Our way is fine. Any questions there? Okay. No. So there's lots of different ways to prove it. Our way was fine. Okay. Any idea about this one?
Okay. So I think I've done this one before, so we'll see. Okay, so the negation statement is that there are finitely many prime numbers,
Mm-hmm.
and then you can list like all the prime numbers, but just add one. So we say P1, P2, P3 is prime numbers.
Okay.
But if you add one, that makes it even, does it? If you add one to a prime number?
It would, yeah. And so,
Does that contradict the statement? I'm stepping after the even part.
so I've called like Pn to be like the largest prime number. So
Yeah.
adding 1 to it would make it an even number, but that wouldn't be a prime number.
No. Add two.
That wouldn't necessarily make it a prime number.
Divide it by something.
The only way...
Oh, why don't you multiply it by something?
What would you multiply?
I don't know. I swear you multiply it.
So I think what you could do is multiply every prime number by each other.
Oh yeah, that was it. Which makes them all a factor of each other. So they're not
Yeah.
prime numbers anymore, are they? Because they have that many factors.
Okay. And then what would happen if you were to add 1 to that?
There would be no. That would be. It would be a prime number.
So I believe so, and because there's no number that is a factor for that,
Yeah.
and therefore that's what it would be. Let's see. So consider the number. This, when you divide n by any of the prime numbers, you get a remainder of 1. So none of the prime numbers is a factor of n. So n must either be prime or have a prime factor which is not in the list of all possible prime numbers. Yeah, this is a contradiction, therefore. Yeah. So if you multiply all the prime numbers together, then add 1, you have a number that if you divide it by any prime number, you will always get a remainder of 1. So either it's a prime number itself, or if it isn't a prime number, then the list of all prime numbers which we just listed is missing a prime number. And so that's a contradiction, therefore infinitely prime numbers. Any questions there? Yeah, nothing easy about these. Okay. So which of these is the negation statement? A, B, or C?
B.
Yeah. What is the negation statement for each of these?
Not all rich people are happy.
Yeah. B?
Is it there is a prime number?
Yeah.
The P and Q prime number and PQ plus 1 is a prime number. The PQ plus 1 isn't a prime number.
Yep.
All numbers of the form 2n minus 1 are either prime numbers or multiples of 3. Not all numbers of the form 2n minus 1 are either prime numbers or multiples of 3.
Yep.
All of the above statements are true.
Uh,
Or
which one?
the second one.
Yeah, all of the above must be false. There's not even one that is true. And they might say at least, but yeah, so they use the word at least, but that's fine. At least one rich person is not happy. There's at least one number. If P and Q are prime numbers, there exists a number of the form that is not prime. Yeah, none of these statements are true. Okay. Okay, let's try this.
Oh, it's true, isn't it?
It is true. You have to prove it by contradiction.
If n squared is odd, then n is even. Is that the opposite?
Yeah.
Okay. Oh, I hate proof.
Yeah.
If n squared is odd, then n is odd. So if n is even, that means n is 2n, isn't it?
So
No, an even number is 2n.
So if n squared, so if n is even, how could you write any even number?
2n.
So I'd just use something else,
2k.
like
2k.
n equals 2k or something, yeah.
So 2k squared equals 2k plus 1.
Well, it will be a...
4.
Well, what will this be squared?
4k squared.
So that's 4k squared, yeah.
4k squared should be an odd number, right?
What could you factorize for that?
2.
Yeah.
So it's a multiple of 2, which makes it even.
So 2k squared is even.
Which contradicts the statement if n squared is odd, n is even. But n squared we just said is even. Because 2k squared is even.
So 2k squared is even. K squared will also be even. I don't know if that, you might not really need that. Because it's a multiple of 2. Let's say n squared is odd, n is even. So n is 2k.
That's a negation statement.
Yeah. So n equals...
What we've just said.
Sorry, what? N squared. If n squared, yes, that is it. N squared is equal to 2 times 2k squared. 2k, so 2 times 2k squared is even.
So n squared equals even.
So yeah, so n squared must be even.
Therefore,
we would say like this is a contradiction.
oh yeah.
Therefore.
It is a contradiction.
So if n squared is odd, then n is odd. Any questions there? Okay. Let's see. Yeah. 2, so n squared equals 2 times 2k squared. So n squared is even. This contradicts the assumption that n squared is odd. Therefore, if n squared, yeah. Okay. Which one of these do you like? Which one of these do you not like?
The last two.
Okay. Let's see.
Okay, if PQ is even, at least one of PQ is even. Is that already a negation statement, or is that just a statement?
That's the true statement that you must prove is true by saying the opposite.
If PQ is even, at least one of PQ is odd?
Is not even, I would say.
Oh, yeah.
If PQ is even, then at least one of P and Q is not even, or could say odd. I'll say odd. Okay.
So if PQ is even, so PQ equals 2n.
So let PQ be equal to 2n. Okay.
Yeah, that's what I've got.
So I think that's going to be a trickier way because that's involving working in reverse. I think it might be easier to say, so with multiplying, P times Q and Q times P is the same thing.
Yeah.
And so it doesn't matter which one we choose for them to be odd. So let's say let P be an odd number. So how could you represent P as an odd number?
2k plus 1.
Okay, so let P be equal to 2k plus 1. What would we let Q be equal to? An even number or an odd number?
Odd.
Why?
Because odd times even doesn't equal even.
I believe it does.
Oh yeah, 3 times 4, 12. Does an odd number?
So we're
Okay, it's not odd, because does odd times odd equal odd?
yeah.
Okay, so then make it even.
So it must be even. So what would we call it?
2k. No, just 2k.
2k.
Okay, so 2k times 2k plus 1 equals 2k.
Okay. Not so fast. 2k plus 1. So
Then just work that out. So
that would be if it was the exact same odd number. So let's just work that out first.
Okay, so 4k squared plus 2k equals PQ.
Equals PQ.
And then you're going to factor that. We just expanded it. You're going to factor it again?
Just the 2.
Oh, okay. 2k squared plus k equals PQ. Which is a factor of 2, so it must be even.
Yeah. So this is a multiple of 2.
Yeah, multiples of word.
Therefore it is even. Therefore PQ is even. Our assumption was if PQ is even, then at least one of P and Q is odd. We've shown that PQ is even. At least one of these was odd.
Is that the opposite of saying that? Is that the negation? The correct way?
I believe so. If PQ is even, then at least one of PQ is also even. Oh, hang on. If at least one...
Because isn't that just the same as saying one is odd?
Yeah, if at least... Yes. So if at least one is even, that means P is even, Q is even, or they're both even. So what's the only way?
If PQ is... What, the only way that it can't work?
Yeah.
They're both odd.
They must both be odd. Yeah, that's the negation statement.
Yeah. Otherwise it just doesn't work out.
Yeah. Then both P and Q must be odd. Okay. Okay, so what could we do?
What do you mean?
How would we... I think we need to redo that.
Oh yeah.
Because they must both be odd.
Okay, so P equals 2k plus 1.
Yep.
Let P equal 2k plus 1. And Q... These both need to be odd. So 2k plus 3.
Yep.
And that needs to equal an even. So 2k plus 3 times 2k plus 1. Yeah, PQ equals 2k plus 1 times 2k plus 3, which must equal... Shall we just expand that first?
I don't think we even really need to, do we? What is odd times odd?
Odd.
Yep. Equals odd. So that means PQ is odd?
Yeah. Which is a contradiction.
Yeah. This contradicts the assumption. Therefore,
if PQ is even, then at least one of PQ, P and Q is even.
That's it. Any questions about that?
No.
Okay, and let's try D.
If PQ is... We just did that, didn't we?
We did C.
Yeah, but didn't we do that one line before we rubbed it out?
No.
Did we not? Oh, that was PQ times Q.
Yeah, this is P plus.
Okay, negation statement would be if P and Q is odd, then at least one of P and Q is even. Wait.
I don't think so.
No. If P plus Q is odd, then at least one of P and Q is odd, so the opposite of that is... both P and Q are even?
Correct. Then both P and Q are even.
So P equals to K. Q equals Okay. Plus 2. An odd number, which is 2k plus 1.
I don't think that's even necessary. P plus Q.
Oh.
What type of number will that give you?
Even plus even gives even.
Yeah. And what did we say in our assumption?
That is going to be odd.
Yeah.
It's not.
So this is a contradiction.
Yep.
Any questions there?
Oh.
So, okay. Trying to see. So they went to Fancy Town. So this is even. This contradicts. So I went by their examples where they. If I go back to this example. Very first example, I believe it was. They said odd plus even equals odd, so I used this type of thing. I didn't use like 2k plus 2k plus 1. If it's good enough for them, it's good enough for me. Let's see. Okay, exam question.
Which one?
All of them.
Prove that if AB is an irrational number, then at least one of A and B is an irrational number. So AB equals A over B?
Yes.
Okay. The negation statement would be if AB is an irrational number, then both are rational.
And I think that, yeah, that's contained. A and B are integers, because that's the definition of a rational number.
Okay. A and B are integers. So do we do the whole times by B thing?
Do I need to use a different letters though? Hold on. I think I might need to use different letters. Let me just go back to when we did this one before. Rational number root 2 equals A over B. So we're saying A over B. So I think I might just need to say C over D, something like that.
Okay. So AB equals C over D.
And C and D are integers.
And then what do you do?
So how did we do this one before?
Times it by D.
Yep.
A, B, D equals C.
Okay. A, B, D equals C. Well, I need to move this one up. So we said root 2 is A over B. We then squared both sides. Second. Okay.
That was different. It was a number. It wasn't just 4 letters.
Yeah, true. So this means that it must be even. So if AB is irrational, then at least A or B. Am I right with the 4 letters here? If AB, then neither A nor B. Oh, okay. So you can break it down.
So A equals C over D.
So you could go even simpler, yeah, because you only have to prove that it's one of them.
A equals C over D. B equals E over F.
So
A
you only have to disprove it for one. So AD equals C. AD equals C.
F equals E. What does that mean then?
Well, if you square both sides, let's see if we go back.
Where C and D are integers. Whoa. A is rational, C and D are integers. And then they did.
Okay.
And they made them the same denominator. So you get D, so it'd be C, and they cross multiplied. Whoa, that's a bit of work for 3 marks.
A equals C over D. B equals E over F. And then they multiply the two things together?
They made them have the same denominator.
So I think they did like statement 1 and statement 2, like simultaneous equations. AB equals C over D times E over F. And what do you get when you multiply those two?
I don't think they multiplied, did they?
CE over DF, like A.
I'll look at the wrong question. Lol. Okay. Yeah. AB equals CE over DF, where CE and DF are integers.
Yeah.
So therefore, AB is an integer.
Therefore, AB is rational.
Yeah,
Because
make
it's,
it rational. Yeah.
it's a rational divided by a rational. What did we say in our assumption? Sorry, what is our negation one? Prove that if
if AB is an irrational number, then both are rational.
If AB is irrational, then yes, both A and B are rational. If A is rational, then it's equal to C over D. If B is rational, then it's equal to E over F. If we multiply the two, we get that. So that AB, or I should say CE over DF is rational. Therefore, AB is rational.
Yeah.
Because it's equal to CE over DF.
This is contradiction.
Yeah.
Oh my god.
Therefore. Okay. B.
That sucks. How much does this come up on the exam?
Sorry?
How much does this come up on the exam? Like how?
It is the first, so you are the first year who will see this on an exam paper. This is totally new. Wasn't in the maths book last year. Yeah, so you guys are have the worst of the worst. You'll be the first year to do this stuff. You're welcome.
So much.
And that's, I think, why, you know, like it's new for me.
You
It's
get
new for your
some
teacher.
questions. If it's
Sorry.
the first time, if it's the first time it's coming from the exam, where are you getting these questions from?
So this is the book written by the people who write the exam paper. So Pearson at Excel, they are the ones who are saying that these are exam questions.
Okay.
And the GCSE is 1 year ahead. And in this summer, some of the questions that were in their book did come up on the exam that had never previously come up. Like I was teaching my students vectors for a hexagon, which had never previously come up, and then it was on the exam paper, and so it's a pretty good.
Wow.
Okay, do it. Despite it being brutally difficult.
Which one are we doing?
Next one, B.
B.
Yeah.
What was the question before that? A, B times.
It was A times B. Yeah.
Yeah. Negation would be if A plus B is an irrational number, then both A and B are rational.
Yeah. Okay, what would we do?
So if the both be, so A equals C over D,
Mm-hmm.
and B equals E over F.
Yeah.
So if saying that C over D and E over F are, like, assume they're like rational.
No. What is A plus B?
A plus B equals C E.
Well, C over D plus E over F.
Yeah.
Okay.
So given the same denominator, which is DF,
Mm-hmm.
so CF plus D over DF.
CF plus.
DE
Yeah.
over DF, all of it over DF.
Yeah.
Which is rational. Equals A plus B.
Yes. So what we needed to say up here, which is kind of assumed, was C,
And D are integers.
C, D, E, and F are integers.
Yeah.
And so what can you say about this fraction?
It's rational.
Yeah.
So A plus B must be, A and B must be rational numbers.
A plus B must also be rational because it's equal to a rational number.
A plus B must be rational. This is a contradiction.
Yeah.
Therefore, A plus B is irrational. At least A and B is irrational.
That's it. Okay. And then 1 mark at the end for this thing. Don't crash. Okay.
A plus B is a rational number, then at least one of A and B is a rational number. Show by counterexample that this statement is not true. If A plus B is a rational number, then at least one of A, B, that is not true. How? That would. What counts as an irrational number? Anything that can't be made into a fraction?
Yes. Anything that can't be written as a fraction a over b, where a and b are integers.
So pi is irrational.
So pi is irrational because it can't be written as a fraction with an integer over an integer. Surds are irrational, like square root of 2, square root of 3.
So if we did so to counterexample, we need to think of two irrational numbers that make a rational number.
I think what we could do, so a plus b is rational.
Yeah.
They said at least one of a and b is rational.
To make it rational, so we need two irrationals to make a rational.
At least one of a and b is rational. Yeah, we could do, they're both irrational.
Yeah, but what two irrational numbers make a rational number?
When you add them. Oh yeah. So what way do you go about this? If a plus b is a rational number, and so that statement is wrong, am I right?
What statement?
That their statement.
Oh yeah,
we have to show it's not true. So then what's the opposite of this? What's the negation?
That if a and b is a rational number, then both a and b are irrational.
I think it might be so what could counterexample it?
Having two irrational numbers make a rational number.
So a is rational. So they're saying a is rational or b is rational.
Yeah. Are squared numbers irrational?
The square root of a square number is what I was thinking, but that would be rational, and they're not surds.
Oh.
So irrational plus irrational making irrational. The only thing I can think of is a square number, but I wouldn't count them as irrational.
Well, can you make them into fractions?
Many possible answers. 2 minus root 2. B is root 2. So they...
That's cheeky, that is.
Why is that cheeky?
That is so... Because they've done 2 minus root 2 is A. And they made B root 2. So when you do 2 minus root 2 plus, well, you just get 2.
So one is plus and one is positive, one is negative.
I didn't even think about that on this.
Okay, so one of them has to be a negative number. That's how it works.
Yeah.
So A or B is negative. Yeah. There you go. Okay, so give me another example then.
Let me check on my calculator before I tell you, just in case. Anything under that format, so like 3 minus root 3 plus root 3.
Then 3. Yeah.
Yeah.
And I think, yeah, and so on. Yeah. Any questions there?
What's 0? Is that a rational or irrational number?
0 is rational, because you could write it as 0 over 1, 0 over 2.
So can't you just do root 3 minus?
You could, or you could even do something like A equals 2 minus root 5 and B equals root 5. Or if you wanted to be fancy, you could do A equals, let's say, 4 minus 3 root 5. And
then
B is Yeah. And so on.
Wow.
Basically, one is negative, one is positive. That's the trick.
Yeah.
So it ends up rational. Any questions there?
No.
Okay. Let's not do proof again for a long time. So let me just take a look at your thing. So all I can say about proof is it just has to be practiced. It does tend to fall into the same thing over and over again for the different types. Proof by contradiction. Okay. Anything in particular you want to do next? Next in the book would be algebraic fractions and so on.
And then now that we've come back, they did this integration thing, and now, like right now, we've just started proof by contradiction.
Okay, so
How I did that.
So
Sorry.
so next time we'll do integration.
Yeah.
Okay. For year 2. Okay. Any questions? Sorry, no. Let's just do a quick recap with this crazy thing, so it doesn't get the better of us. Okay. So this one, proof by contradiction that there's no greatest odd integer. So we, I think, did it properly, which was, you think of 2k plus 1 as the largest odd integer. You add 2, then you can factorize out 2, but then it has a plus 1 at the end. This part is a multiple of 2, so it must be even. Plus 1, it must be odd, so, and it must be bigger than the other one. And then they cheated and said odd plus even equals odd. So that's what I did in the future, and then they went back and did it the other way.
Yeah.
If n squared is even, then n must be even. So that was a similar thing. We let n be equal. Sorry, we said n is odd, so it's 2k plus 1. We square it, we factorize out 2, and it has a plus 1 at the end. Infinitely many prime numbers. List the prime numbers, including what must be the biggest prime number, because we're doing the negation. Multiply them all together. Plus 1 means it would be a remainder of 1. So either this is a new prime number, or it is not a prime number, and there's a prime number missing from our list of all prime numbers, which is a contradiction. Therefore, I think these we were okay for. This was very similar to the other one. Just you let it be 2k because it's even, and square it.
Don't take the drink.
Let's see. P, Q. Yes. This one, odd times odd, gives us odd. That one was okay, I think. And D. I think that one was okay. So I think the irrational one was the tricky one. Let's see. So root 2 can be equal to A over B. Both of those are integers. Let's see. A squared equals 2b squared. A must be even. I think the irrational ones are the tricky ones, but I think we got there in the end with the irrational ones.
Yeah.
I think those are the ones to practice. Yeah. How was that for you, Saba?
That was good.
Well, good is a strong word. We got through it. Okay, so yeah, next time integration for year 2. Any questions for me in general?
No.
Okay, I think proof, you just have to practice it. I think actually we're okay for most of proof. It's really just the irrational stuff that has to be, and it always tends to be you write it as a fraction. You either add, subtract, multiply, or divide those two fractions, and then you end up with something that's odd or even or rational